We've now covered launches with upward projections with the horizontal, and in the previous lesson we analyzed the motion of a projectile launched horizontally. In this lesson, we will launch the projectile with a downward projection as shown, or we could think of the projectile launched from a tower where the launch angle is negative. So we have a projectile launched from a tower of height 100 meters and launched with a speed of 70 meters per second at an angle of 20 degrees with the horizontal, but below the reference line. So we consider theta as minus 20. Let's first find the time of flight. We apply the second equation of motion along the y-axis, and we have y minus y0 equals v0yt plus half at squared. Our reference line is a horizontal line passing through the launch point A. The initial y displacement y0 is 0, since at that point in time the projectile is on the reference line. The final y displacement is minus 100, where 100 is the height of the tower and the negative sign since it lies below the reference line. The initial y component of velocity v0y is 70 sine of minus 20, and this would turn out negative because of sine of minus 20, and you can see that upon resolving the initial velocity vector, the y component would point downwards. The acceleration is minus g since it is in the downward direction. Solving the quadratic for the time t, we get the time t as 2.68 seconds. If you compare this with the earlier lessons where we had upward projections, or in the previous lesson where we had a horizontal projection with the same initial speed, you will find that the time of flight will be the lowest in this case where the projection is downwards. This is because the initial velocity y component is downwards and in the direction of acceleration. So the height h will be covered faster. When the projection is upwards, the time of flight will be the highest. Let's find the range next. To find the range, we use the concept that the horizontal velocity component of the projectile, or Vx, remains constant throughout its flight due to the absence of acceleration in the x direction. And you can see here that Vx does not change with time. The range, therefore, is simply the x component of velocity times the time of flight. The x component of velocity is 70 cos of minus 20, and the time of flight we had just computed as 2.68 seconds. With that, we get the range as 176.28 meters. Now we will compute the y displacement when the projectile is 130 meters from the launch point. Here we use the trajectory equation, and it is valid even when the angles are negative. So let's make the substitutions. We substitute 130 for x, minus 20 for theta, and 70 for v0, and we obtain y as minus 67 meters. This is the y displacement when the x displacement is 130 meters. With this, we have now covered all the different types of projections that take place from the top of a tower, that is, above the reference line, the case of horizontal projection or along the reference line, and in this lesson, the projection below the reference line. Regardless of the type of projection, whether with positive, 0 or negative angles of launch, we can always find the time of flight by applying the second equation of motion along the y-axis. But you have to be very careful with the signs. Also, we have seen how to obtain the range in each case. The trajectory equations are also always valid. So if we have to find the y displacement for a certain x displacement, we can make an easy substitution into the trajectory equation.